for
Thank you.
your talk. And at this point, we'll move on to Sinka from the University of Leicester. Sorry, I've assigned you to several universities so far, Sava. You are there, okay? You can hear me and I can hear you, can I?
Yes, good morning. Let me stop other people's sharing screen if I can.
We can do that in a second, but if you just put your screen up, that would be great. And Sava, if I just introduce you briefly, so Sinka, I mean, I guess to some extent the grass always looks greener on the other side, or perhaps even on your own side. And what Sava's going to talk about is a virtual formulation laboratory. Trying to formulate granulated materials is certainly non-trivial, and something that when I've occasionally dabbled in it has been considerably unpredictable. So what this project set out to do was very ambitious, and we'll be very interested to hear, Sava, how progress has gone on. So over to you at that point. Thank you.
Okay, good morning again, and thank you very much, Simon. I eventually managed to bring our presentation up to screen. I hope you are able to see it.
We can see that fine and can hear you good. So.
Thank you. So our project also has a very long title, but every word matters, and I think it's useful to read it very slowly at the beginning, because it's actually a very good summary of what we do. So we are developing a virtual formulation laboratory, which is a software tool used for the prediction and optimization of manufacturability of advanced solids-based formulation. So before introducing the project team, I'd like to say that many of you will know that our colleague, Dr. Rob Berry from Greenwich University, has passed away earlier this year following a serious illness, and this was a huge for everybody in the project. Let me introduce the project team. So we are a consortium of 4 universities. At Leicester, it is myself from the Department of School of Engineering now, and Professor Ruslan Davidchack from the School of Mathematics, working with our postdocs, Ben Edmans and Nicodemo Di Pasquale. At Leeds, we have Professor Moshtaba Ghadiri and Jadong Jha, known as Jha to everybody, assisted by Dr. Mehrdad Pasha, and a range of visiting scholars who have joined the projects at different times. At Greenwich, we have Professor Mike Bradley and now Dr. John Cummins, assisted by Hamid Salehi and Vivek Garg, PhD student. At Imperial College, we have Professor Jerry Heng, assisted by Vikram Karde and Isabella Phillips. It is our pleasure to announce that Professor Jerry Heng has become professor just recently. His appointment has just been confirmed by Imperial College. So we also have very good news in terms of our colleagues. Our project is also supported by a good range of companies, including in no particular order, the CPI, National Formulation Center that Simon mentioned, P&G, GSK, AZ, Nestle, KP, Brookfield, Brightest, PSC, Griffiths, Freeman, Chemours, Edem, JM, and AbbVie. You can see they cover pharmaceuticals, food, catalysts, fine chemicals, a range of powder processing industries, remembering that our project focuses on solid formulations. So the software tool, what we do in this project, we are developing this software tool called Virtual Formulation Laboratory, which takes inputs at 3 levels. It can take input from bulk powder level, so it can take inputs from particle level and also from molecule level. And our aim is to predict the manufacturability indicators, which in 4 areas. These are powder flow, segregation, caking, and compact strength or breakage. what we do in the project is actually the two yellow vertical lines on the left. So we are linking molecule to particle and particle to bulk powder information. So we are basically developing the science that enable us to make those links and therefore make predictions at different levels regarding the manufacturability of these formulations. The project, like all 7 projects presented today, is of course funded by EPSRC, and we are grateful for their support. In a nutshell, we are developing the science to link particle to bulk and to link molecule to particle. In this framework, the characterization of adhesive interactions, which is very important not only for the previous project, as Jean mentioned, but also for solids, and we have dedicated 40% of our effort into characterizing and predicting these interactions. You will hear about this in a moment. And finally, we connect the results in the development of a toolkit. So at this point, we are going to take turns. I'm very pleased to report that our project is still going strong. We had 5 PDRAs, 4 of them are still in employment in their original institutions. We are all of us here today, and we are going to go to take them one by one through to highlight the main achievements of their work. I would like to, so we'll start with the surface energy, and the first speaker is Vikram from Imperial College. I will be just turning the page. Vikram.
All right. Thank you, Csaba. I hope you are able to hear me.
Very good.
Yeah, thanks. So at Imperial, we are working on surface energy characterization of particulate solids. We believe surfaces are very important as they control interactions like solid-solid, solid vapor, and solid-liquid. Here we are defining surface energy in terms of thermodynamic sense, which is free energy change per unit area at constant temperature and pressure. Now, there are different techniques to measure surface energy of solids. Here we have used a technique called as inverse gas chromatography, which is IGC. It is the reverse of traditional chromatographic technique. So we have an unknown sample packed in a glass column, and we pass known vapor probes, and we determine the interactions of these vapor probes to calculate the surface energy. Now, the solids are energetically heterogeneous, have energetically heterogeneous surfaces. So depending on different planes, different facets, they may show like, for example, contact angle measurement. Next, please. Yeah, so here we are using a new approach called as finite dilution inverse gas chromatography to determine the surface energy heterogeneity of these solids. So we get data in the form of surface energy as a function of surface coverage. Next, please. As we know that different processing operations like milling, sizing, functionalization can affect the surfaces of solids. So we are looking at the surface energy evolution of solids here with the processes like milling and surface functionalization done through a salinization approach. Next, please. Yeah, so here we have the data for mannitol. So mannitol we have used as a model material here for processes like milling and surface functionalization. So as you can see, for the milled mannitol, we see an increase in the surface energy heterogeneity indicated by the green line as compared to, say, unmilled mannitol material indicated by the red line here. For surface functionalized mannitol surfaces, functionalized with hydrophobic moieties, we see a decrease in surface energy heterogeneity or almost an homogeneous surface here as indicated in the magenta and blue colored lines. Next, please. Next, we have also studied interparticle structuring in binary mixtures. So structuring of component particles within the mixture can affect the surface properties, and important to consider in formulations. Here we have considered binary mixtures of glass beads and mannitol. Two different scenarios were envisioned. The first was random mixture, where there was weakly interacting components, weakly interacting particles between the mannitol and glass beads. And the second was structured mixing, where there was a coating of one component over the other, exhibiting almost a guest host type of interaction. So basically very strong interactions. And when we study these mixtures in IGC, we can see a definite trend. So in case of structured mix, we see a homogeneous profile for the surface energy heterogeneity profile. Excuse me. For the random mix, however, we see a heterogeneous surface indicated by the red line here. Now, further to this, we also deconvoluted this IGC experimental data using computational model based on Boltzmann probability distribution to get a quantitative estimation of different energetic sites or the distribution of energetic sites for these components. So on the top right-hand corner, you see distribution of different energetic sites for glass beads, binary mixture, as well as the salinized built mannitol components. And we see that for the binary mixture, the energetic sites have moved to the left toward the low energy component in case of structured binary system. This was also confirmed using SEM images. So the top two images show a case of random mixture where there's no coating, whereas the bottom we see coating of glass bead particles with mannitol particles. So to conclude, next please. So to conclude, we prove here, or it is evident that structuring of component particles is very important when considering powder formulations. So, next, I'll hand over this presentation to Ruslan and Nicodemo from University of Leicester.
Thank you, Vikram. Thank you, Csaba. Can you hear me?
Yes.
Okay, good. So we have looked at surface energy, but from the molecular simulation perspective. So the hope was that we could link with IGC results and understand the mechanism of how surface energy is formed from the molecular level. The next slide, please. However, we did recognize quite early on that there are still some challenges about the characterization of surfaces and different types of information that can be extracted from measuring surface properties in molecular simulation. So initial part of our research, we settled in establishing some relations between surface stress and surface free energy, which were well known, but the debate was still out there what exactly these things measure. So we verified on a very simple Lennard-Jones crystal that indeed the understanding of surface stress as work per unit area done by the surface which is stretched is linked indeed to the surface free energy, which is work of creating a unit area of the surface or interface. Next slide, please. These are just the details of how we measured these properties for the LJ system. I'm not going to spend time describing it, so let's just go on to next slide, please. So what we have done, which is more relevant, to actually measuring surface properties for VFL, was to look at the test system mannitol, which you saw in Vikram's talk, and looking at different surfaces and measuring surface energy using our so-called cleaving method. And for a long time, we actually try to understand what was happening, because our results were quite different from what Imperial was getting from their measurements. And only recently we realized that there is actually a very big difference in terms of which force field is being used. So when we use all atom force fields, which expected to be more accurate, we were actually getting these big discrepancies. But more recently, we decided to try united atom models from Gromos. And it turns out that they seem to give results which are much more consistent with IGC results. So next slide, please. So this is just the thermodynamic integration. So essentially what we are doing in the cleaving method is transforming a system where we start with bulk, so periodic boundary conditions on the sample in all directions, and then we gradually switch off interaction on the surface, which is on one of the surfaces. So in this case, the result is for a surface which is normal to the b-axis. And switching happens gradually. So we have a parameter which goes from 1 to 0. So 1 means full interaction across the surface, and 0 means no interaction. So we're actually creating, so we essentially go from bulk geometry to slab geometry. And if we integrate these curves, assuming these transformations are reversible, so we can go back and forth and get the same curves, which in this case they are. So they have been tested going from 1 to 0 and then from 0 to 1. So when we integrate these curves, we get contributions to the surface free energy. And you see that curves do look different depending on whether you use united atom or all atom. And we also have two different structures from the Cambridge database, 09 and Demantel. And they also, you can see some differences there. We can also, the two contributions that we have in the surface energy comes from Lennard-Jones interactions, which could be related to sort of van der Waals type interactions, and Coulomb of interaction of residual charges in the models. So you go next slide, please. And this is the summary of the results that we have so far. They are not yet completely foolproof, so we're still checking whether there could be any errors that need to be fixed. But what we already observe here is that ATB is all atom and Gromos is united atom. The two structures, DM and DM09, and different orientations. So we have Lennard-Jones component, and you could see here that the results for Lennard-Jones component are quite close to the dispersive component in IGC. And then the main challenge that we had before, you can see for all atom models, we have very large Coulombic interactions, which was rather unexpected. And when we moved to united atom models, then these interactions again became much smaller, especially for DM09 structure. And again, it might be consistent with a polar component of surface free energy that is available from IGC experiments. So it looks like we are converging on the results, and we are hoping that molecular simulation can have predictive power in terms of characterizing surface free energy for different molecular crystals. I think this is last slide. Yes. Okay. So I will pass on next to Ben and Csaba.
Hello, can you hear me? Yeah. Okay, Csaba? Yeah. Yes, thank you. So I've been working with Csaba on the compaction aspect of the VFL project. So we've been carrying out particle scale numerical simulations to investigate the relation between mechanisms involved in powder die compaction and the development of strength in the powder compacts produced. So for us, a key concept linking particle and bulk descriptions has been contact laws. So if you can move to the next slide. Thanks. So first we aim to develop numerical contact laws for compressible particles at large deformations. So by compressible, we mean a material which can exhibit irrecoverable, rate-independent reduction in volume, which is characteristic of pharmaceutical excipients. So to investigate this, we carried out a parametric finite element study, and inside this finite element model, inside the elements, we implemented a novel generic compressible plasticity model, which is characterized by three dimensionless parameters. Firstly, the ratio of Young's modulus to compressive yield strength, the ratio of strength to compressive strength, the ratio of shear strength to compressive strength. And by looking at the low displacement results of these simulations, these are the simulations of simple spheres in contact. We fitted these results to a closed form normal force displacement relation shown on the right, which has got three parameters. We then established the relation between the three parameters of the material model and the three parameters of the contact law model. We also did some qualitative work in which we investigated the development of different types of zones within the particles as they deformed, the zones which exhibit different types of plastic flow behavior. So this work has been published in Mechanics of Materials. Go to the next slide, please. Secondly, we also wanted to look at the unloading response of particles which exhibits elastic, perfectly plastic material behavior. So a lot of investigators assume that the unloading response of an elastic plastic particle is linear, but at large displacements that's not the case. So we characterize unloading response with both a stiffness parameter and a non-linearity parameter. And again, to investigate this, we carried out parametric finite element studies. Here, the parameters of the models used were the ratio of elastic stiffness to yield strength, the Poisson's ratio, and the dimensionless displacement incurred before unloading. So we were able to establish this relationship saying how the unloading stiffness varied with the three input parameters. And we also got some results for the unloading non-linearity, and we were able to explain the trends shown. So this work has now been accepted for publication in Powder Technology. Thanks. Yeah, if we can go to the next one. And the final piece of work is the development of a model for predicting the strength of powder compacts from the particle and surface properties. This model is nearly finished. We just got to do the last stage of it. It contains three component models, all of which have some basis or evidence in the published literature. First being a fragmentation population balance model, which describes how a powder sample undergoing dye compaction had the particles fragment and become smaller. A deformation model, which incorporates elasticity and plasticity of the particles into the model. And finally, an adhesion model saying how adhesive force develops between the particles as compaction increases. So the last thing we've got to do in this model is a calibration, and we're calibrating against some experimental data which we have for assemblies of aluminium spheres, glass spheres, and wax spheres. So that's the end of the compaction part.
So Saba, we've got 5 minutes for the rest of the talk. I don't know how many more people are up.
2 more.
I think it's Hamid from Greenwich next.
Yeah. Good morning. I'm representing Greenwich. So in Greenwich, we follow 3 main objectives of VFL, namely fluid quasi-static condition, plastic flow caking, and rolling segregation. All these topics actually help us to understand better flow behavior of particulate material, and data and the model we develop for each specific objective actually is going to use or was used in the VFL toolkit. So next slide, please. So for flow in quasi-static condition, we partly develop or modify a method initially developed a few years ago at the Wolfson Center in drop test method. It was initially developed to measure the detachment of the flavor from the potato chips. So we modify that. How it works, actually, we firstly make the tablet of the material, and then we coat with a few grams of material with the G3 over the tablet, and then drop it from different height, and we measure the amount of mass that detached. So we have the acceleration ratio and also the detached mass, so we simply can calculate the interparticle forces. So we did quite a considerable number of tests with different materials and in different heights. Also, we changed the tablet from, for instance, glass, metal, or some other material. And we finally came up with the empirical model based on the bond number or adhesion force that can be used to predict the flow behavior of the particulate material at the earliest step of formulation. So next slide, please. So the second part was the plastic flow caking. For this part, we also developed a very, very simple test method in two different sizes. The smaller size could be used only few grams of the material. So we use this tester to measure the caking strength of the material as a result of consolidation and temperature at a longer duration. So the good point about this tester actually is that we have a defined shear plane. So the results are quite repeatable compared to the conventional caking tester. So also the material it needs is very low, and it's very easy to construct and it's cheap. So we made an empirical statistical model to investigate the effect of different variables on the caking strength of the material. So, and it is, okay. So next slide. So segregation. So we focus on rolling segregation. We use the equipment developed a few years ago at Wolfson Center. So it consists of a mixer at the top. So we mix the material and then slowly discharge the material in this inclined surface. We allow the material to form a heap, and then from each part of this compartment, we can take the material and investigate the size, particle size distribution or shape. Okay. You know that for rolling segregation, it tends different particle size and shape located in different part of the heap. So one way to avoid this is to make the material is more cohesive. But how cohesive it should be? If we make it very cohesive, then the material is not flowing. So our aim was to mainly understand this critical cohesion that leads to avoiding the segregation, but at the same time not affecting too much the flow properties. We use different grades of calcium carbonate that gives us different level of cohesion, and of course they have different sphericity. So we investigate the effect of cohesion on the particle size distribution at different height, different location of this compartment, as well as the sphericity at a different location. So these are the part from the Greenwich, and Mehrdad Pasha is continuing with from University of Leeds. Thank you.
We're really sort of out of time at this point. I think we're going to have to move on to conclusions.
Well, I mean, can I pass, instead of conclusions, can I pass it to Mehrdad? I think I already said the conclusions at the beginning in terms of what we are trying to do. It would be good to quickly go through. He's got a very short presentation on it.
Okay, quickly, fine. No, it's just where I realize people are dropping in and out because it's difficult to be online meetings. It's been fantastic to see the team. So anyway, over to Mehrdad for a very quick one. Sorry about that, Mehrdad.
I'll try to be quick. So our approach from Leeds was to look at the flowability of powder mixtures at high strain rate conditions. So I would say we had ambition to come up with a mechanistic model in order to predict the flow behavior at high strain rates, but eventually we've got there. So the aim was to identify individual properties of individual components in terms of single particle properties and link that one to the bulk powder flow behavior, and finally to come up with the product performance. So Csaba, if you move to the second slide, because I talked about this. So next one. So we came up with a methodology to represent the cohesivity of the powder mixtures by bond number, which we call it mixture bond number. And we investigated different methodologies for averaging the bond number. And this approach is using interaction of the components rather than to contain the bond number of each component. So in a binary mixture, we have 4 interactions. So component AA, AB, BA, and BB. So that is how we are calculating the mixture bond number. And the bond number is basically force of adhesion over gravitational force. So we have already published this one in powder technology. So now I'm going to show you the results. So if you go next. So we compared the 3 averaging techniques: arithmetic, geometric, and harmonic mean. And when we plotted these in terms of data we get from FT4 rheometer, we managed to get a unification of the data for the flow, specific flow energy as we measure from FT4 as a function of arithmetic mixture bond numbers. So we can represent the cohesivity of the powder mixtures in terms of arithmetic mixture bond number. So next was to come up with a rheological model. So if you move next, Csaba. So we've done also in DEM, we've done a lot of stress analysis on the same type of mixture. So to give you a brief, we have investigated more than 100 mixtures in our study. And what we found, we developed a master curves or a generic curves where we represent the data in terms of non-dimensional shear stress, which you see on the left-hand side, which is shear stress divided by this inertial stress, as a function of inertial number, which is the ratio of microscopic deformation timescale and inertial timescale. And we've got a unification for all sorts of mixtures as well as different strain rate conditions. And from that, we can drive the kinematic shear viscosity curve. And now we have a generic curve where we can develop our toolkit based on that. So if you go next. So in terms of the generic curves, I'm talking about on the left-hand side, you see the non-dimensional shear stress, and we have a master curve where increasing the shear rate, we are going down the slope. Increasing the hydrostatic stress, we are going up the slope. And increasing the bond number, again, we are going up the slope. And also from that, also we can drive a similar curve for kinematic shear viscosity. So by having these relationships, so if we move next, we have developed a toolkit which is based on a MATLAB GUI where we can input, we can define the number of components we have in the mixture and the property of individual individual components as well as interactions. And then finally, we can drive the curves without running any experiments. So this toolkit would help in terms of early stage formulation product development, where you can identify the bad formulation from good one. So that gives you the operational window of how much of what should be your mixture ratio between the components in order to get a good flowability, which represent, for example, if you're having a screw conveyor, then what type of mixture or how much of the free flowing component you need to add to the mixture in order to process the formulation. So now I'm going to pass on to Csaba to.
So thank you very much indeed, and thank you all for your patience. We are going to have a dissemination event at some point next year. Thank you again.
Great, Csaba. Thank you very much. Thank you very much, everybody. Yeah, we're just running against time. So thank you, everybody, for using the questions on the chat. We've got some really good ones going there. If you can make sure you label it so it's obvious who you're replying to or whose question you're answering, then when we pick them up at the end, that would be really great. But please keep the chat going, the conversations going on there. I think we're all learning from each other, so great. Thank you very much.